All right, let's dissect this paper on the Platonic Representation Hypothesis. It's a pretty bold claim that AI models are converging towards a shared, almost Platonic representation of reality. What's your initial take on this central hypothesis? Does the evidence presented seem compelling, or are there significant flaws in their reasoning?
The hypothesis is certainly provocative, and the authors make a strong case for representational convergence across different models and modalities. Their evidence, based on kernel alignment metrics and observations of model stitching success, is intriguing. However, the Platonic representation itself remains somewhat vaguely defined. The idealized world they construct in Section 4, while useful for mathematical analysis, might not fully capture the complexities of real-world data and learning.
Right, the idealized world. They posit a sequence of discrete events, observed through bijective, deterministic functions. How realistic is that assumption, especially when considering the inherent noise and ambiguity in real-world data? And how does this simplification affect the validity of their conclusions about convergence?
It's a significant simplification. Real-world observations are rarely bijective or deterministic. Sensors are noisy, and different modalities capture different aspects of reality. Their mathematical argument hinges on this bijectivity, implying that the information in all projections is equivalent to the information in the underlying world. This isn't true in practice. The conclusions about convergence are therefore likely to hold only approximately, and the degree of approximation is hard to quantify.
They discuss several potential selective pressures driving this convergence: task generality, model capacity, and simplicity bias. Let's unpack these. How convincing is their argument that increasing task diversity and model size inherently leads to representational alignment?
Their argument is plausible. More tasks mean more constraints on the representation, narrowing the space of possible solutions. Larger models with greater capacity are more likely to find a solution that satisfies all constraints. Simplicity bias, whether implicit or explicit, further pushes models towards simpler, more generalizable representations. However, the interplay between these factors is complex and not fully understood.
The authors propose that the converged representation is a statistical model of the underlying reality. They even suggest that certain contrastive learners converge to a representation of the pointwise mutual information, PMI, kernel. How robust is this claim, and what are its limitations?
The connection to PMI is interesting and potentially insightful. Contrastive learning methods often implicitly learn relationships between data points, and PMI captures co-occurrence statistics. However, the author's mathematical derivation relies heavily on their idealized world assumptions. In real-world scenarios, the relationship between contrastive learning and PMI might be more nuanced and less direct.
They discuss implications like the potential for easier cross-modal translation and adaptation. If models are converging to a shared representation, it would make sense that transferring knowledge between modalities becomes simpler. But how much of this is already happening, and how much is still theoretical?
Cross-modal transfer is already a significant area of research, and the success of models like LL-all-L suggests that some degree of shared representation is being achieved. However, the ease of translation isn't guaranteed, and the authors claim that language models could achieve grounding in the visual domain without cross-modal data is a strong assertion that needs further investigation.
The paper also acknowledges counterexamples and limitations, such as the fact that different modalities may contain different information. How significant are these limitations, and what are the biggest open questions remaining?
The limitations are substantial. The idealized world assumption is a major one. The fact that not all representations are presently converging across all domains is another. Measuring alignment itself is a challenge, with different metrics yielding different results. The paper raises more questions than it answers, which is often the case with groundbreaking research. The degree of convergence observed in their experiments is also relatively low, leaving room for alternative explanations.
They mentioned the potential for scaling to reduce hallucination and bias in LLMs. Is this a realistic expectation, or is it overly optimistic?
It's a plausible expectation, but not a guaranteed outcome. Scaling might reduce some types of hallucinations and biases by better reflecting the statistics of the training data. However, other types of biases, particularly those stemming from societal biases embedded in the data, might persist or even be amplified.
The authors touch upon the sociological bias in producing AI models. How much does the human-centric focus of current AI research influence the observed convergence towards human-like representations? Could other forms of intelligence lead to different representational structures?
The human-centric focus is a significant factor. Many AI systems are explicitly designed to mimic human capabilities, which naturally biases the research towards human-like representations. It's entirely possible that other forms of intelligence, optimized for different tasks or environments, would develop vastly different representational structures. This is a crucial point to consider when interpreting the results of this paper.
They also discuss the hardware lottery, suggesting that the success of AI models depends on the compatibility of their design with available computational architectures. How does this factor into the observed convergence trends?
The hardware lottery is a real phenomenon. The architectures we use heavily influence the types of representations that are easily learned. This could contribute to convergence, as researchers tend to gravitate towards architectures that are computationally feasible and perform well. However, it also limits the exploration of alternative representational spaces.
The paper highlights the possibility that special purpose intelligences might not converge. How does this reconcile with their central hypothesis?
This is a crucial caveat. The hypothesis primarily applies to general purpose intelligences, optimized for many tasks. Special purpose systems might develop highly efficient representations tailored to their specific tasks, which may not align with a general representation of reality.
The choice of alignment metric is also a point of discussion. They primarily use mutual nearest neighbor, but acknowledge the limitations and explore other metrics in the appendix. How critical is the choice of metric in interpreting the results?
The choice of metric is extremely important. Different metrics capture different aspects of representational similarity. The author's choice of mutual nearest neighbor emphasizes local similarities, which might be more relevant than global similarities captured by metrics like CKA in certain contexts. The appendix showing results with other metrics is crucial for a complete understanding.
Finally, what are the most significant contributions of this paper beyond the central hypothesis itself?
The paper's main contribution is to highlight the intriguing possibility of representational convergence in AI models. It also provides a framework for thinking about the selective pressures driving this convergence and explores the potential implications for cross-modal transfer, hallucination, and bias. The detailed analysis of contrastive learning and its relationship to PMI is also a valuable contribution. However, the limitations and open questions are equally important and should be kept in mind when interpreting the results.
A fascinating discussion highlighting both the potential and the limitations of this intriguing hypothesis. Thank you.